Hello, this is Stephen Nesheb again, and I'm here to help you out with exercise number 4 from the Visualizing Thermodynamic Surfaces Computational Guided Inquiry. So the idea on this one is we want to look at deviations of a thermodynamic surface of an ideal gas compared to what we think is a more accurate version, which is the Van der Waals gas. So that's what we're going to do here. Now, it's going to be easiest to just modify the script file ts3.py that we already created for that, and so that's kind of where I'm going to start off here. And I've already this is the same ts3 where we ended up with last time, and there we are. So what I'm going to do first of all is I want to go and save as this thing is ts4. So that I don't clobber everything that I've already done with TS3. Okay, and so there's that, and I've also brought up TS1 because that's got some of the Van der Waals formulas and stuff in it that we might need. So for TS4, let's see, I'm going to want to recreate everything that I've done already for the ideal gas. I think I'm going to change the notation on this a little bit, so just to remind myself that this part here obviously was for an ideal gas, because what I want to do next is just kind of copy this, and instead of for an ideal gas, this is going to be for a Van der Waals gas. And now recall we had to have Van der Waals parameters here, so these were mine that I used for Krypton, and you'll probably want to have something else. So we can put that somewhere, anywhere above there. So we got the A and B parameters. Now the pressure for every point on the gas, this is not the Van der Waals gas formula. Let's see, what was that Van der Waals gas formula? Oh, it was right here. So I think I'll just copy this one. I'll have to make a few modifications because I need to have this calculated along a grid. But I'll go ahead and copy this. So, right, so it's nRT. Oh, I forgot to put an n up here, didn't I, before? But n was 1, so it's not a problem. Here's the Van der Waals gas, nRT divided by that. But now I don't want the temperature, I want the gridded temperature. Okay, and I'll do the same thing here, and the same thing here. So that's gonna calculate that. And now, you know, it's a good idea to just run things to see if everything is looking okay. So I'm just gonna go ahead and run it, and it hasn't produced any new graphics just because that's all I asked it to do. But it looks fine. I didn't get any error messages. Okay, so now the next thing that you might want to think about is how are you going to graph the new Van der Waals thermodynamic surface? It's going to be something just like this, but you're going to make a fairly slight modification. Maybe you'd like to give that a shot. Okay, assuming you're back, here's what I'm going to do. I'm just going to copy that whole thing wholesale and paste it. And I'm going to put it on a new graphics window, so I'm going to call that number 2. That's going to affect that line and that line. Let's see, and now I want to do it, of course, on the same grid, but rather than do P grid, I'm going to do the gridded result for Van der Waals, VDW. Okay, I think that should be okay. And now I think everything else can stay the same. Maybe I want to change the annotation to remind myself that figure 2 is going to be the Van der Waals result. Let's see if that does anything. Okay, so now I see I've got figure 1 and figure 2, and figure 1 is the old ideal gas result, and figure 2 is the Van der Waals result. That's fine. They are only very subtly different. I can't even tell the difference between these two. So I'm going to go on and do the third piece of this, which is to graph the difference between those. And maybe you'd like to give that a shot before I move on. Okay, well, let's see. I've got the ideal gas result. I've got the Van der Waals result. And Well, how about we take the difference between them? So get the difference. Okay, so I don't know, I'll just give it a new variable name called pdiff. Okay, and that's going to be equal to P of the ideal gas minus P van der Waals. Okay, and that should be fine. Actually, what we wanted was a percent difference, so I'll just say call that an error. That would have to be equal to P diff divided by the van der Waals result and times 100. Okay, so that should work, and I'm just going to assume that it's going to work, and now I'm going to go and graph that last result. Okay, and so rather than figure 2, I'm going to have that appear in figure 3, and rather than graph the van der Waals result, I'm just going to call that the error. That's the thing that we calculated up here, I think. Yes, the error. And I better change this result to just percent error. Percent error. Oops. And let's see whether this works. So there's figure 1, figure 2, figure 3. And well, I think that we got what we were looking for.